of n squared. The upper bound over estimation of how much work is being done is n squared. So my question is, does that mean that this algorithm is theta of n squared?
Yes.
Yes. That is the correct answer. We know it cannot be more, but we also found an upper bound, which is proportional to that. Since this is the upper bound, and it cannot be less, it is theta n squared. Even though we cannot solve this using the master's theorem, but the recursion tree was very helpful. All right. Does that make sense? Is that helpful?
Okay, I get a question. From 1.5 n squared, you see from the level 2, zero level, from the level 1 to infinity, so take like 0.5 n squared, does that mean? The fourth level take n squared. From the level 1 to level infinity, you
Yes.
take 0.5 n squared, right?
You're saying how can it be true? How can it be true? You're saying this is crazy. You did this here. And you're saying for infinity, that's all you accumulate. Well, the reason for that is because the amount of work is decreasing geometrically. Or in other words, put it, the amount of work being done at the next level is decreasing exponentially.
But how about the level 1?
Ah, okay, I knew I was going to forget something. So, now with this one, we ran into a problem. So, right here, just like we did here, we can do the same thing. Let's solve this one. So we have, this is going to, the first term is, so our term is going to be 1 plus 3 over 2 plus 3 over 2 squared plus, right? Whatever we have here, 3 over 2. Let's call it to the h. And all that stuff is being multiplied by n. And what is h? That's our big level. So what happens here is that the value of this is going to be 1 minus a minus a times 3, 2 to the power of 12h over 1 minus 3 over 2, which is negative 1/2. So this is going to be equal to 3 over 2 to the h minus 1 times 2. So basically it's going to be 2 times 2. Now, the problem with this is that if h is a large number and we let h go to infinity like before, the problem is 1.5 to infinity will go to infinity. It will not converge. Why not? Because the amount of work here, the work is increasing exponentially. Here, the work was decreasing exponentially. Does that make sense? So for this one, we were not so lucky. But for this one, we were kind of lucky. So it's interesting. So you're looking, so the bottom line is if you have a geometric, here's the general rule. If you have a geometric series, and you always, if you find this pattern, you will find this geometric component. If you find this geometric series, and the ratio is less than 1, it will converge as you go to infinity. And if it converges to a constant, then the upper bound is going to be a constant times your n squared, n cubed, whatever you have. It's going to be, you're going to be able to get that upper bound. But if the ratio is more than 1, it's going to diverge. Which doesn't mean that the work goes to infinity. It just means that if we let the fake tree grow to an infinite level, the fake tree gets exponentially infinite. The real tree doesn't do that. The real tree ends. In the real tree, we can't let height go to infinity. We could here because the rate of growth was less than 1. And that converged the infinite series, but here it's not. So we cannot use the same technique because of the fact that this geometric growth rate is getting bigger. Which I think was, so basically the work is getting 50% bigger each time. Each time. So we can't sum infinitely. So the sum is finite, but there's no nice way of getting it. All right, any questions about that? All right, easy? Not so easy, okay. All right. Did we talk about graphs in this class? We didn't talk about graphs here, right? Okay, so I'm trying to do everything I can do about starting the notes today so I can stay on the board, which is what I enjoy anyway, so. So let me erase this, I'll do something a little bit different. So let's look at another problem. I'll give you a problem and we want to try to solve it. So we know, let's think about binary trees. So binary tree is a tree that has at most 2 children. A node can have at most 2 children, right? So what I'm interested in is finding out how many different ways we can create a binary tree with a set of nodes. So let's say we have 15 nodes. How many different trees can we create? Well, the 15 values could be anything, but I don't care about the actual values. I have 15 different values. I'm interested in what the tree looks like, specifically the shape of the tree. And to understand the shape of the tree, we should understand how trees get their shape in the first place. Okay, how many of you are familiar and remember binary tree insertions algorithms? How many people would like to refresh that idea? Okay, good. That sounds like we're on consensus. All right, so here's the idea. So before we talk about this interesting thing, let's talk about the binary trees in general. So the binary tree idea is very, very simple. Let's just, for the sake of simplicity, we'll assume that the binary tree is holding only keys. We're only putting keys into numerical keys. So initially, the binary tree, if you will, is just a pointer to nothing. So it's an empty tree. If the tree is empty, what does that mean? Everybody's getting President Trump alert? I was waiting for that. Oh boy, oh boy. Everybody's worst nightmare. All right, so we have an empty tree here. Yeah, he's just interrupting our daily lives now. It's not enough that he does it in the media. He has to do it on your phone. All right, so initially the tree is empty, and it looks like this. Essentially, we have a root pointer which is pointing at nothing, right? Okay, so then I'm going to insert the first node. So whatever the first node becomes known as the what? Becomes as the root. Okay, so let's say that value, for the sake of argument, has a value of 30. So 30 becomes the root. Now this is a binary tree, but specifically I'm going to be talking about BST, which is called a binary search tree. So in a binary search tree, all nodes lesser than me go to my left, all nodes bigger than me go to my right. And that helps me search things. When I go to the right, I know that everything's going to be bigger than what I just saw. And when I go to the left, it's going to be less than what I just saw. Okay, so now let's say we want to add another node into this tree. So let's say the node that we want to add is going to be 10. So we already have the 30, which is our root, and now we have a 10. So we go in here and we check out the key, and the key is 30. And we say, okay, a 10 is 10 less or more than 30. So therefore, it's less, so therefore this node gets added to the left. And let's say the next node I'm going to add, so basically my sequence of adding was 30, followed by 10. Let's say I'm going to add 8. when I add 8, notice that it's going to be 30, followed by 10, and then it's followed by 8. So the tree is beginning to take a shape. And let's say we're going to add one more, and that value is going to be 9. So in that case, it's going to be less than 30, it's going to be less than 10. It's going to be more than 8, so therefore it's going to become here. So the tree will look like this. All right. Let's, so you understand what's going on here. So now, is that a good tree? It's not a very good tree. And the reason it's not a very good tree is because searching it basically will require possibly n comparisons to find what we're looking for. So let's take a look at this tree right here. This tree also is not very good. In fact, it's as bad as it can be in terms of being efficient. But this tree was created with an insertion sequence of 30, 10, and 8. This is how, so we basically create a binary search tree with this insertion sequence. First value goes to the root, and then we go by lesser to the left, greater to the right. We get lesser, lesser, lesser. Here, that's what we got. Some people think that these are just bad keys. They're just tough keys. They're going to get a good tree out of it. But actually, if you take the same keys, and you start with 10, and then you have 30, and then you have 8, the tree will actually have a different shape. Because the root is going to go to 10. First insertion. Bigger than 10. And then when we come in again, 8 is less than. So now we have a nice looking tree. What do we call that tree? It's a balanced tree. We like balanced trees. And the reason we like balanced trees is because their height of a balanced tree is pretty much minimum to the number of keys. So for example, if we, now this tree specifically, we're going to call it full. Full means not only is it balanced, but every level has the most values. Every level that exists in the tree has the most nodes it can possibly have. So a full tree could have how many nodes? 7, right? So this one has 3. This one has 7. If I add another full level, how many do I get? 15? In general, the number of nodes is going to be 2 to the k. That's 1. So if we had 1,023 nodes on a, let's say, full tree, full DST, how can we find out what is the height of the tree? Well, if you look at this one, which has 15, right? If you add 1 to 15, it's what? 16. If you take the log base 2 of 16, you get 4. 1, 2, 3, 4. Here you had 7. Here you had 7. Before you had 7. If you had one more, you had 8. Log base 2 of 8. 1, 2, 3. So this one right here, what will be the height of that if it was a full BST? It was basically n plus 1, and we'll take log base 2, n plus 1. So what's LG of 1,024? 10. So what does that mean? Well, it basically means that this tree would have a height of 10, and n is 1,023. That means whatever I was looking for, and you look for a tree by comparing and going left or going right. If you had this tree, whatever you're searching for, you would do no worse than h number of comparisons, which is 10. But if you had a tree that had a very bad shape, it looked like this, you know, which can happen, then, and if this height was also 1,024 and you had 1,024 nodes, then you might be searching as deep as 1,024, 1,023, 1,022. On average, you're going to be searching what? if you have n nodes in a shape like this, you're going to be searching how many nodes on average? N. You're searching n nodes. So it's beneficial. It's beneficial to have a tree that has a balanced shape. Now, this tree here has 15 nodes, right? And we said it was full. But if you can have a full tree, for example, what if you're missing one node or two? Now how many nodes do we have? 13, right? Can 13 be full? No, but it can be balanced. Balanced means that the nodes at the deepest level, that deepest level may be missing some nodes, but no other levels are missing any nodes. So only the deepest level can be missing any nodes. Every other level is full. So if you have a tree of 13 and you add 1, it's still balanced. Okay? But if you add 1 here, it's no longer balanced. Because this is the deepest level, it's missing some. This is the next one level, is missing some. No good. So here, we only have the deepest level missing 1, so we have this. Still balanced, full. Now if we add a node, is it balanced? Yep, still balanced, but not full. It can't be full, right? It can't be full unless the number of nodes is equal to this one. Okay? Now if you think about it, if you have 7 nodes, so let's say this is our tree. I'm going to just draw the numbers for the keys. That's a very bad tree with the 7 nodes. But actually, if you take this node, so the insertion sequence, by the way, here would be 2, 4, 7. You get the idea, right? If we change the insertion sequence to 8 being the first one, and then choosing 4 and 18 as the next ones, actually it doesn't matter what follows them. It would be a full tree. Because if 8, 4, 18 come in first, you're going to have 8, you're going to have 4, you're going to have 18, and then what else you got? You got 22, well 22 is going to go here. You got 11, 11 is going to go here. How about 22, 11, 22, 11, how about 11, 22, 11, 22? How about 2 and 7? 2 is going to go here. How about 7 first? It's going to go here. So you can see that the sequence of insertions determines the shape of the tree. Which leads us to an idea that how could we take a tree which is in horrible shape and turn it into a balanced tree? What kind of an algorithm could we come up with to turn a tree in very, very bad shape into a balanced tree? And I'll let you destroy the tree. Let's just create another one that's balanced and get rid of the old tree. So the first thing we need to do, we need to dump out the keys of the tree. So for example, there are how many people are familiar with tree traversals? Tree traversals. Okay. Okay, so maybe I'll just show quickly. So I'll show what a tree traversal looks like. So a tree traversal is basically a way to visit every node in the tree. And when you visit the node, you can do whatever you want to it. You can print it out, you can modify it, etc., etc. So let's say we have a tree that looks like this. Let's say we have a tree that looks like this. Let's say we have 30, and then we have 20, and then we have 10, and then we have 5, and then we have 15, and then we have... What's the biggest number I can have here? 29. Why 29? Because it has to be less than 30 to get here. So this would be 20, so let's make it 28. What's the biggest number I can have here? 29 again, because I can't have 30 because it was 30. We're not going to worry about duplicates. We're not going to allow duplicates. But so 29 would be the biggest one. Is there a smallest number here? Can it be 19? No, because 19 would go here.
21.
So let's say 21. So let's make it, for example, 24. It's okay? Okay, and then let's say add this one more key here. Let's say it's going to be 40. Okay, let's say what we want to do is we want to turn this into a balanced tree. How many nodes is that? 3, 4, 5, 6, 7, 8. Let's actually take away one of these nodes to make it 7, because 7 can be full. 7 can be full. So the algorithm to traverse a tree. So first of all, we're going to say that this pointer right here is the root. So we can call something in order traversal. In order traversal means that we're going to visit every key of the binary search tree in key order. So for that we require a BST. This is a BST, binary search tree. So we're going to say in order traversal, and I'm going to send as a parameter the root. So the root comes in. So this is the in order traversal algorithm. We have, so we receive a node, right? IoT in order traversal. The first thing we're going to do is we're going to say if node not equal to nil. So if the node is not a nil node, we do nothing. Then we're going to do something. If that's the case, what we're going to do is we're going to go in order traversal, and we're going to say node, and we're going to say the left child. The left child is the node to the left. So if the root comes in, since the root is not nil, we're going to go IoT with the left child. Recursively. Then we're going to visit the node, and that could mean just print it, do something with it. And then we're going to do in order traversal node right child. Let's see how that would work. So that's the end of this algorithm. So this is the start up here, and this is the end. So let's see how this would work. So somebody says, okay, do an in order traversal of the root, so they sent me the root. So that means it's going to be this node right here. The node is not nil. So remember, I am at level 0. Level 0, because somebody called me level 0. So at level 0, this is the node. So this is node sub 0, node level 0. Not equal to nil is true, so we go IoT node dot left child. IoT is recursive. IoT is recursive, so therefore the left child becomes the new node at level 1. So this becomes the node level 1. This one right here. This node comes in, it's not nil, it's a 20. So therefore we go in order traversal, again recursive call, node, left child. We go to level 2, recursion. Sending in the left child of 20, so that becomes node, level 2. The 10 comes in, it's not nil, therefore we go node, left child. So this one again causes another recursive level, sends in this node into recursive level 3, so this is node at level 3 recursion. Level 3 recursion receives this 5 node. Node is not equal to nil, therefore it sends the left child of the 5. Well, because the left child of the 5 doesn't have any children, we're going to assume that it's sending a nil node, or a nil pointer. So what happens is, this recursive level 3 sends a nil value to level 4. The condition is false, which means that this is skipped and the function returns immediately back to level 3. Last time we were at level 3, we recursed with a nil pointer, so now we visit the node, which means we print the 5. Print the 5. What level are we in? We're at level 3. And now we're going to go to IoT level 4 with the right child of the 5. The right child at level 4 will be nil, condition is false. Level 4 will return to level 3. Last time we were at level 3, we went to the right. So we're done. So we go. Excuse me. We go back to level 2. Last time we were at level 2, we went to the left. So now we're back in level 2. We're going to visit the node. And that's going to be a 10. And then from level 2, we're going to recurse to the right into level 3. Nil returns. When we return from level 3, we return to level 2. Level 2, call the right child. So we finish here. Excuse me. So we return to level 1. Last time we were in level 1, we went to the left. So now what are we going to do? Went to the left, so now we're going to visit. So we're going to visit the 20. And after the visit from level 1, we're going to go to the right, which is a node, level 2. Not nil. So we're going to recurse here. From here, we're going to go to the left. Level 4, nothing going on. Come back. Visit. We go to the right, there's nothing to do. We're going to come back to 28. Last time we were at 28, level 2, we went left. After going left, we visit. So that's going to be 28. We try to go to the right, nothing to do. We come back to level 2. We are done at level 2. We come back. We're done at level 1 because we're just coming back from the right. We're always done. Then we're going to come back to level 0. Last time we went to level 0, we went left. So what do we do at level 0? Visit the node. Look at that. After we visit the node at level 0, we go to the right. We go to the left, nothing to do. Come back here, visit. We go to the right, nothing to do. We come back. Done, done, done. And that's the visitation in order. So what we can do is we can do this in order traversal and write this sequence of numbers into an array or a file, whatever we want. So now the second question is, how do we recreate this tree so that it is balanced, or in this case even full? Okay, so how do we write this algorithm? Well, I think the idea, which do you think would make the best root for this tree? Which key? 24 would make the best one. Why? Because half the values are less than that, so they're going to go in the left subtree. And then half are bigger, so the subtrees will be balanced. So it makes sense to choose 24 as the root, making the left side the left subtree and the right side the right subtree. And then recursively speaking, what do you think will be the best left child for the root? 10, because 10 will have a balanced subtree underneath it for level 2. best one for the right side, 30. You get the idea? So how do we write this algorithm? How do we write this algorithm? By the way, any idea what the complexity was of doing this? What's the complexity of the traversal? Did we visit every node? Yeah, so therefore it can't be any less than n, because we got to go to all, we got to go to every one of the n nodes. Was a log involved there, or was a n squared involved there? No, pretty much we kind of went like this. You know, over here. That's it, we kind of just went around the tree once or twice. So theta n. So the complexity of this is n. Now, the next complexity is going to be how do you build a balanced tree? The idea is we're going to pass an array. Let's just keep it simple. We'll pass an array of values. Okay? So the first thing we're going to do is do what? We're going to insert into the tree. So we're going to create a new empty tree. We're going to create a new empty tree. And then we're going to get this array. Empty tree. And so now we're going to have this build balanced. That's too many words. BB. Build balanced tree. BBT. Okay, and the array, we're going to call this array A. Okay, so the array A is coming in. How many elements does this array have? Well, let's say it has indexes from A to B. How does that sound? So this is little a, and this is little b. So build balanced tree, what are we going to do first?
Insert after that, or the index?
Insert.
Insert the root, which is going to be the midpoint of that.
Okay, well, okay, fine. What I want to do is I want to make this procedure a recursive procedure. So, how do we make sure it's a recursive procedure? Because recursive procedure, basically I'm going to insert this and I'm going to insert, you see what I'm saying? So the recursive procedure is going to do an insertion and then it's going to have two recursive calls. Right? Sure. Okay, so, so how do we make sure that we are not in the base case? Okay, or at least that A is not greater than B. Because if A is equal to B, that means we have one node, and we can insert that. Remember, the only thing important